Good afternoon, class. We're back to 351 Chemical Process Principles, Module 3.1 Material Balance Calculations. We'll be looking at introduction, material balance. Under that, we'll look at differences between steady state and non-steady state operation. We'll look at setting up material balance equation, overall and component balance equations. We'll also look at procedure for solution to material and energy balance problems. And we'll look at solutions to material balance problems for systems at steady state, processes without chemical reactions, and we'll conclude. Cost minimization is an important factor in industry that it constitutes a key quantitative aspect termed as optimization. So when we talk about optimization, what are we actually looking at? You want to optimize your yield, you want to also optimize, your profit, because any industry that is not running on profit is most likely will be shut down. It won't take that time, they will close. Now, chemical plant design and operation requires calculation of quantities of materials and or energy to be supplied, produced, or removed to or from either a whole plant, part of a plant, or some unit. The solution to all such problems is based on the concept of material and energy balance. So for you to set up any chemical plant, you have to work out what quantity of material are you going to use. Can you afford that? What quantity of product are you expecting? Is that going to be enough? Staff strength, availability of raw materials, workforce, so many things. And this is, in other words, we do material balance in our lives. In economics, you can call that something that looks like a scale of preference. You have to arrange things, know what is going to come in, how much are you making, how much can you afford to spend. So we must do a balance, whether it's material or energy, in the company for us, for the industry to function well. So a fundamental concept for virtually all calculations in the chemical industry or chemical process technology, and it's very crucial for every student to master this concept because it is used in problem-solving calculations, as we're going to see shortly. Now, the material or mass balance concept deals, among other things, with the calculation of all mass flow rates into and out of a plant or a process unit. You see, that's very, very important. We must know all the mass flow rate that is going in and out, either the entire factory or a particular process unit. Of course, if we do that for different process units one by one, we'll be able to now do that for the entire factory. From the calculations, the quantities of reactants and products, the volume of vessels, piping, pumps, and other equipment are estimated. Energy balance concept is a principle whereby the energy entering a unit or item of the plant is equated to the energy leaving the plant. Although the techniques for handling material balance and energy balance problems are similar, we will treat material balance problems first before energy balance. Material balance. Material balance is defined as a study showing the origin and ultimate disposition of all materials used. So you can see it shows us the study of all the materials used. We must know where they are coming from, and we also must know how they are used, and where they are going into products. It is the accounting of material flows and changes in inventory of material for a system. It is the basis of process design. Now, material balance assists us in determining the quantities of raw materials required and the products produced, just like I said, planning for process design, the economic valuation of process control, process optimization, and the study of plant operation and troubleshooting. So you can see that material balance is very, very important. In fact, if you don't do material balance, then you're most likely going to have very serious issues concerning your production process. Generally, for material balance, we have accumulation is equal to input minus output plus generation minus consumption. And as a generic term, material balance can refer to a balance on the system for the following: total mass. It can be for total mass. It can be for total moles. It can be for mass of chemical compound. It can be for mass of atomic species, mole of atomic species, or mole of a chemical compound, depending on the particular problem we want to solve. It can also be for 2, 3, or more of these at a time, so we'll take that one after the other. With respect to total balance, the generation and consumption terms are zero, whether a chemical reaction occur or not. Hence, accumulation is equal to input minus output. Again, with respect to balance on the moles, if a chemical reaction occurs, if a chemical reaction occurs, you most likely will have to consider the generation and consumption terms. So if chemical reaction occurs, then we must consider the generation and consumption terms. Now, differences between steady state and non-steady state operations. Now, we'll try to differentiate steady state, non-steady state. Now, for example, for steady state conditions, whether it's density, temperature, at any given point the system remain constant over a measurable time. But for non-steady state, these conditions will continuously be changing over time. Input mass or input mass flow rate equals output mass or output mass flow rate. That is garbage in, garbage out. Input is equal to output. But for non-steady state, input is not equal to output. For steady state, there is no accumulation of mass in the system. That is, accumulation or rate of accumulation is equal to zero. But for non-steady state, there is accumulation, and of course, that's why our input is not equal to output for the non-steady state. There is accumulation, and then it can be positive or negative accumulation. For steady state, material balance equation is applicable over finite time, but for a non-steady state, material balance equation is applicable over an instant of time. Again, for steady state, material balance equation is written in integral forms, whereas material balance equations for non-steady state is written in differential forms. And then for steady state, again, material balance equation is solved without integration, whereas for non-steady state, material balance equation is solved by integration. Now, how do we set up material balance equations, overall and component balance equations? Multi-component systems. For multi-component systems, material balance equation, integral as well as differential, must be written for 1, the total mass of all material in the input output, and in the process unit. And 2, the mass of each individual component in the input, output, and accumulated in the process unit. Overall balance equation. Material balance equation in terms of total mass of all material going into and out of the system. Component material balance equation. This is the equation written for an individual component. Overall and component balance equation, they together play important parts in the solution of material balance problems. Now, material balance in all situations and for all systems. 1, involving liquid, solid, gas mixture of these, with or without chemical reaction, batch or continuous systems operating at steady or unsteady states, with co-current or counter-current flow, with or without junction points such as recycle, bypass, purging points. So we can use material balance for any of these to solve our problem. Solutions to material balance problems for systems at steady state. Now, for systems at steady state, we identify the various process units in the given problem. Then draw the flow sheet clearly. See, we must draw the flow sheet clearly, showing the process units and identify process flows. Then you indicate at the appropriate points in the flow sheet all the given data. When you draw the flow sheet, then we must indicate at the appropriate points, the streams, the amount of stream flow, and all that. Then we use algebraic symbols, capital letters, to represent all overall mass flow rates. Of course, very important, we choose basis for the calculation. We must choose a basis. We'll still see that. We use the selected basis, the mass fractions of the component, and the values of the overall material flow rate in the input and output streams, including those now represented by algebraic symbols, to evaluate masses or moles and kilogram mole quantities of the component. Then for each process unit, set up the overall and component material balance equation for each component. Then solve the simple simultaneous equation by usual algebraic methods. We'll of course look at an example where we apply all these things you are listing to solve the problem. We'll have processes without chemical reaction. Now, in all processes, the total mass is conserved, but in purely physical process, the mass of each species is also conserved. Hence, the material balance can be written for each species as well as the total mass. However, one of these equations will not be independent. So let's look at an example. This example is a distillation column which operates as shown in the diagram below. We're asked to calculate the composition of the bottoms and the weight of the alcohol lost in the bottoms. Now, look at the diagram. It's a distillation column. What is going in is 1000 kg of feed, and that feed is made up of 10% ethanol and 90% water. You can see that 90 plus 10 is 100. So it enters the distillation column, and the distillate is given off 60% ethanol, then 40% water, and weight of the distillate is 1/10 of the feed. So you see, since the feed is 1000, if you multiply by 1/10, it means that the distillate will be 100 kg. Now, bottoms, we're not told anything, the composition of the bottoms, but we know that as the distillate is going, there must be something that is remaining as a residue. Now, solution. We're pulling down one by one. First of all, we draw the diagram, we draw the flow sheet for that problem, and you can see our distillation column, you can see our feed, you can see the bottoms. We have used the feed as capital F, the distillate as capital D, the bottoms as capital B. So we can see what we have. We are given the feed, we're also given the distillate, but the bottoms we have X ethanol and we have Y% of water. We don't know that, and that's what we want to calculate. Now we're using the basis as 1000 kg of feed. Remember that the feed is 1000 kg that is going in. Now the system, of course, is distillation column. So weight of distillate, like I said, is 1/10 multiplied by 1000, which gives us 100 kg. Therefore, weight of ethanol in the distillate, we're now doing a component balance for ethanol in the distillate. Remember, it's 60%. So 60/100 multiplied by the total of the distillate, which is 100, gives us 60 kg. The weight of water in the distillate, following the same, is 40/100 multiplied by 100, gives us 40 kg. But the total material balance will be B plus D is F. Remember, F is entering, D is leaving as distillate, B is leaving as bottoms. So F must be equal to B plus D. And that is B. We don't know B, but we know D, distillate, which is 100 kg. We know F, which is 1000 kg. So solving that, we'll get B as equal to 900. Now you can see we have gotten B. Now we'll do ethanol balance. Now what is ethanol balance? We want to check the ethanol in B, the ethanol in D, and the ethanol in F. So you can see in the bottoms, we have X/100. We don't know what X is. Multiplied by B plus, in the distillates, is a 60%, 60/100. Multiplied by D. Of course, in the feed, it is 10%. So 10/100 multiplied by F. So we now solve that. And when we solve that, we have X as equal to 4.444. Of course, we know that X plus Y will be equal to 100. So Y will be 100 minus 4.444, which gives us 95.556. Hence, the required solutions are: composition of bottoms is 4.44% ethanol and 95.556% water. Of course, the amount of alcohol lost in the bottoms is, we know the quantity of ethanol in the bottom, the percentage is 4.44, so 4.444 divided by 100, our B is 900 kg, multiplied by 900 will give us 40 kg. Yeah, sorry, appears like this particular module is, the timing is a little long, but not bad. We're trying to explain all these things so you will understand. We've been able to look at steady state operations, material balance calculation at steady states without chemical reactions. We've looked at examples to illustrate, and we'll stop here. Thank you very much for listening, and I hope to see you in module 3.2. Thank you.